Hello, guys. Welcome back on African Motives. Still working on industrial electronics N3, working on revisions on DC and AC theory. We have a question that you're going to focus on, question 2 of November 2020, which was a comparison. It was actually having two questions on AC and DC. So we've got the first part on DC and the last part on AC. So we are going to focus with these questions and see. So the first part we're given on 2.1, fig 1 shows a circuit with a battery and resistors. So we are given, in this case, this circuit that we are given with the battery. In this case, we are given the V, which is the 12 volts at this point. And also, we are to note the signs that we are having, the sign in terms of the flow of our current from the positive terminal. We've got our negative here. So the current is flowing from the positive, which is this current that is given as I1 plus I2, which is in this branch. We are going to have this current flowing in this branch, which is given as I1. In this branch, it is given as I2. So this is how our currents are presented. So we're given that with the use of the Kirchhoff's laws, can we calculate the current in the 5 ohm resistor? That is the current in the 5 ohm resistor. If we are to take note, in this case, this is our 5 ohm resistor. And the current flowing here is current 1 plus current 2. So that means we are to determine current 1 and to determine current 2. That is what we are supposed to do. All right, and we are given the loops to consider. Use the first part. We are given the loop BAF EB, that is from B to A to point F, point E, back to the point B. This is our loop 1 that we are going to consider. So let us just have this so that we can have our equations. I'm just going to push so that we can properly see the part that I'm going to work with. I'm just going to focus with this part alone. This route is the one that I'm going to take. We are given BA, that is from point B to A to F. All right, let me put it this way. That is to F to E and back to the point E. So this is the route that we are going to consider in this case. All right, so that is the first part that we are given. So here we are going to have loop 1, which is loop B. So we're given this as BAF E back to the point B. All right. So according to this loop, we can see that, remember that from a Kirchhoff's law, the voltage source, which is this V, is equivalent to the voltage drops from this loop that we are given, this closed loop that we have. So which means from B to point A to point F to point E, we have same current. That is, we have one current that is flowing from B, A, F to E. There is current 1 which is flowing in this circuit, which is I1. So this is equal to the product of current times the resistance. The resistance from B to A to F to E, we've got two resistors, R1 and R2. So we're going to combine these two together, R1 plus R2. So that's a voltage drop that we have. We move on from point E up to point B. We are following the same route of current, and we have got only I1 and I2 with the resistor. That is our resistor R3. So we are going to have current, the product of current, which is current I1 plus I2, to the resistance, which is R3. That's a voltage drop. So that is from this loop, we have formulated an equation. So you can insert the values. Our V, which is the voltage supply of 12, is equal to I1 into R1 plus R2. So we have R1, we have R2. So you can add these two. That's R1 is 4, R2 is 10. So it's going to be 4 plus 10 into I1 plus R3. We have R3 in this case, which is 5 ohms into the two currents. So it's going to be 5 into I1 plus I2. So this is what we have. So we can expand the brackets where there are brackets, adding where we can add the 4 plus 10 is going to give us 14 in this case. So here we are going to obtain 14. All right, so this is going to be 14 I1. Then we expand the brackets by 5 times I1, which is 5 I1, 5 times I2, which is 5 I2, like this. So you can collect like terms. That's here. We've got current 1 and current 2. So you're going to add 14 plus 5, which is going to give us 19. So this is going to be equal to 19 I1 plus we are left with current 2, which is 5 I2. So that's the equation that you're going to have, which is 19 I1 plus 5 I2, which is equal to 12. So we've got the first equation from the loop that we are given as B, A, F, E, B. So we move on to the second loop that we are given so that we can formulate an equation again from this loop that we are given as B, C, D, that is from B to C to D to E and back to point B. So I'm going to write these loops. I'm going to push this aside so that we can present properly. So this is the loop that we are given. We are given to take this from the loop. This is our loop 2, which is given as B, C, D, E to the point B, like this. All right, so let's indicate this part. That is from B to C. So we are taking this route from B to C in this route. That is to C to D. Then E to B, that is from B, D to E. Then it goes back to B like this. All right, so this is our second loop that we are going to consider in this case. All right. So from this loop, still having the same concept of the voltage supply being equal to the voltage drops in each branch that you're going to have. So let's consider from the point B. We want to start at point B here. So from point B to point C to point D to point E, there is the same current. It's a series circuit. So the same current that is flowing from B to C is the same current flowing from C to D is the same current flowing also from D to the point E, which is I2. So we are going to have current I2 times the resistance. So the resistance that is affecting this series path from B to C to D to E, we have got two resistors, R4 and R5. So we're going to add these two together. That's R4 plus R5, like this. Okay, we move on from point E to point B. We are still moving in the same direction of the arrows. The arrow that we're given, we are moving in the same direction. So it's going to be a plus. So we've got I1 and I2 with resistor R5. So this is going to be plus current times resistance. That's current I1 plus current 2. This is our total current times the resistance, which is resistor R3. So we're going to multiply to R3. So we have formulated an equation that we are going to apply or that we are going to use to just insert our values. Our V is 12. So 12 is equal to R4 plus R5. We've got R4. We've got R5. So we're going to add 6 plus 7 times current 2 plus I1 and I2. We do not have. We've got R3, which is 5. So this is going to be 5 into I1 plus I2 in this case. So you can expand, simplify, whatever that you're given. 6 plus 7, this is going to give us 13. So that's 13 I2 plus 5 times I1, that's 5 I1, 5 times I2, which is 5 I2. So we are going to collect the like terms I2 and I2 together. That means we are going to have 12 is equal to this part of I1 is not affected with anything. So we are going to remain with 5 I1 as it is. But collecting these terms for I2 and I2, we've got 13 plus 5 in this case, which is 18. So this is going to be 18 I2. All right. So we have an equation that we have formulated from this loop that we can even rewrite as 5 I1 plus 18 I2, which is equal to 12. So this is our second equation that we have formulated from this part. All right, so we're going to take these two equations so that we can solve the first one that we had from the first loop. This is our first equation, and we calculated our second. Remember, the purpose is to calculate I1 and I2 so that we can calculate I1 plus I2, which is the current through the 5 ohm resistor, which is R3. So that is the purpose. All right. So taking the first equation, this is your first equation. We are going to have our first equation. Okay, let me just write it here so that we can solve this part together. So we are going to have our first equation, that's 19 I1 plus 5 I2, which is equal to 12, all right? Then we have got our second equation, the one that we have here, 5 I1 plus 18 I2, which is equal to 12, all right? So this is the one that you're going to use. In this case, we have got 5 I1 plus 18 I2, which was equal to 12 in this case. So with these two equations that we have, we are going to solve for I1 and I2. All right, so let's solve depending with which part do you want to solve first, or do you want to calculate first? In case of, let's say I want to find I1 first by using elimination by substitution method. If I am to find I1, that means I am going to eliminate I2. So in that case, I'm going to eliminate I2. So to eliminate I2, that means I'm going to interchange these two. I'm supposed to have the same coefficients so that I can eliminate I2. So I interchange these numbers 18 and 5 on I2, meaning to say on top, we are going to multiply by 18. On this second equation, we are going to multiply by 5. We interchange these two on I2 since we want to eliminate I2. So it depends with which part are you to eliminate. If you wanted to eliminate I1, in order for you to calculate I2, that means we are going to interchange 19 and 5 on I1. You can eliminate I1 by that. All right. So let us multiply and see what you're going to have. So this 18 is going to multiply everything in the first equation. Then the same thing with 5 is going to multiply everything in the second equation. All right. So that's 18 times 19, which is going to give us 342 I1. Then we've got 18 times 5, which is going to give us 90 I2. So this is going to give us 18 times 12 on the other hand, which is going to give us 216. The same thing with 5 is going to multiply everything in the second equation. So that is 5 and 5, which is going to give us 25 I1. Then is 5 times 18, which is going to give us a positive 90 I2. Then we move on to the same thing, 5 and 12. In this case, this is going to give us 60. So we have our equation 1, our equation 2, with the I2 having same coefficient, in this case 90, 90. It's a plus on this case. So if the two signs are the same, a plus and a plus, you subtract. Whether it's a minus and a minus, you subtract. That means I'm going to subtract the second equation from the first equation, or equation 1 minus equation 2. So this is what you're going to have if we subtract. That's 342 minus 25, which is going to give us 317 I1. 90 minus 90, that's a 0, which means we have eliminated I2. We remain with the constant terms, which is 216 minus 60. So this is going to give us 156, dividing by 317 both sides so that we can determine the value of I1. So that means we shall have our I1 as that's 0.49 211. So this is going to be 2. The 1 is not going to affect, so it's going to be a 2 amps. So this is what we have as our current I1. Yes, you can write this in milliamps if you want, but we are not told about writing this in milliamps. We're just calculating our currents. Okay, so having I1, we can use any of the given equations that we have here. We've got the first equation, the second equation. You're just going to pick any one of these equations so that you can calculate I2 in this case. So in this case, I'm going to use the second equation. That's 5 I1 plus 18 I2 in this case, which is equal to 12. So from this second equation, I can substitute any equation of your choice, guys. All right. So you have I1, which is 0.492. So you can substitute in this case. That is going to be 5 times I1, which is 0.492. So you can multiply these two, which is fine, or you can just leave it like that so that you simplify everything at once. So you can transpose the product, these two, to the left-hand side, to the right-hand side, so that it can be a minus. So this is going to be minus 5 times 0.492, or you can multiply, then you subtract from 12 or whatever that you're going to have, then you divide by 18 both sides so that you can remain with I2. So I2 is going to be equal to the resultant that you're going to have from this part here from your calculator. All right, so from your calculator, this is going to give us something like 0.53. So that's 0.53 in this case, amps. So that is what you're going to have. Or you can convert to milliamps depending with your understanding or your values that you are using. So this you can write in milliamps, or you can just leave it as I2 as it is. Okay, but this is not the question. Let us consider our question and see what you're asked. The question here was to calculate the current through the 5 ohm resistor, and you said through the 5 ohm resistor, the current that is flowing is I1 plus I2. So we are going to have this sum of currents now, that is the current through the 5 ohm resistor. So you shall have this as therefore the current through the 5 ohm resistor, is going to be equal to the current 1 plus current 2. So that's current 1 plus current 2, which is current 1 that was 0.492 plus our current 2, which is 0.53. All right, so this is what you're going to have in this case. So we simplify this value. So you're going to have something like 1.022 in what? In amps. So this is going to be the answer now for the current through the 5 ohm resistor in this case. So you have to be careful with the question that you're given. Answer the question. The question is asking you to calculate the current that is in the 5 ohm resistor from the Kirchhoff's law. So these are the part that you're supposed to take. We move on to the other part. So this was actually 11 marks. So on number 2.2, we are now given a fig in this case to consider, whereby we are given fig 2 shows a series RLC circuit. We are given the values of the inductor, the resistor, and the capacitor in this case, together with the voltage and the frequency of 50 hertz. So the question here is direct, guys, to calculate the inductive reactance, and that's 1 mark for that. Okay, so we know that our inductive reactance can be calculated from the inductance L that we are given in this case. All right, so this is a 2.21, where we know that XL is equivalent to 2 pi FL given from your formula sheet. So you can substitute your values. That's 2 pi times the frequency, where we are given the frequency in this case of 50 hertz. So that's 50 times the inductance, where the inductance L is given as 356 millihenries. That is to the exponent of -3. That's millihenries. So we can have our XL in this case. So XL is going to be 111,840698, which is going to be 41 in ohms. All right, so that was the question, direct like that. All right, so the other part of the question 2.22 was to calculate the capacitive reactance. All right, also the capacitive reactance we are given from our formula sheet. So from C, which is our capacitance here, we can calculate our XC. So XC from your formula sheet is given also as 1/2 pi FC, whereby we can sometimes, okay, we might be given the formula for capacitance, then you make XC the subject. All right, so this is XC is equal to 1/2 pi times the frequency, our frequency that's at 50 hertz, times the capacitance, which is 8 microfarad. So micro, that's times 10 to the exponent of -6. So this is going to give us XC in this case. All right, so if we are to simplify properly our XC, we are going to obtain 397,88735, which is 887. ohms. So this is what you're going to have to 3 decimal places. We have got the value of XC, then the total impedance of the circuit, all right? The total impedance of this circuit that you're given. So remember that this is RLC. So we have to compare, because this impedance is a phasor sum from the resistance and the inductance with the capacitance that we have. So we have to compare between these two values. You can see that XC is greater than XL. So that means our formula is going to be given as, so we are saying XC is bigger than XL or is greater than XL. So the value for impedance is going to be the square root of R squared plus the bigger value minus the smaller value. So it's going to be XC minus XL, this time to the exponent of 2. So this is the proper formula that is going to give us the total impedance, which is the square root of the resistance. We are given from our circuit, the resistance being 15 ohms. So we're going to apply or to use 15 ohms. So this is a 15 squared plus XC minus XL. So our XC, that is 397,887 minus our XL, which is 111,841. So this is 841, everything squared. So we're going to square everything under the square root. All right. So make sure that you apply or use your calculator properly in this case. That is going to be 286. So we put 286,43902. So this is going to be 9. Okay, so that's our total impedance in ohms. And also be careful in terms of the units that you're going to have on your final answer. Impedance, the same as resistance, measured in what? In ohms. Then the total current on 2.24, calculate the total current. So from the total impedance that we have of the circuit, we can calculate the total current. Remember so this is 2.24. Remember that the total current is equal to the voltage over the impedance. So that means our total current is going to be the voltage supply of the given circuit that we have. In this case, we've got a voltage supply of 110 volts. So this is the one that we are going to apply. So we're going to use 110 volts. So we've got 110 over the total impedance, which is 286,439. So that is our total current of the circuit in this case. All right. So we are going to obtain 0.38402 and so on. So this is going to be 4 in amperes, which is amps. So that is 0.384 amps. All right, so we've got our total current of the circuit. So that was the part of the AC circuit that you are given in this case. All right, let's check the other part of the question. All right, do we still have another part? Because seems like we still have another part on the, okay, so the other part is on 2.3. So this is actually another question, which is 2.3. So on 2.3 is actually another question, which means that part is done. So on 2.3, we are now given a coil with an inductance of 5 henries and a resistance. We are given a resistance of 25 ohms is connected in parallel to a capacitor with a variable frequency supply. So once we are given a variable frequency supply, that means it is at resonate. So we are dealing with a resonate, a circuit that is at resonate in this case. All right, so take note, we are given that it consists of an inductor and a resistor. In this case, we are having a circuit. So we've got a resistor and we have got an inductor in this case. So this whole part of the circuit is further connected in parallel to a capacitor. So there is a capacitor. So sometimes they might draw this circuit for you, but in this case, they are just giving you the information. So from this part, we are now given that it is connected to a variable frequency supply set to 12 volts. So this is the voltage supply that we are having in this case. All right, so we are having a voltage supply of 12 volts with a variable frequency. So our V, that is 12 volts, and we are having a variable frequency, that is the resonant frequency that we do not know in this case, the resistance and the inductance and our capacitance in this case. So that is what we are going to have as our circuit. And we are given these values, the inductance, that is 5 henries. So this is, we are given as 5 henries, the resistance at 25 ohms, the capacitance, which is at 250 nanofarad. So this is a nanofarad. So the first question was to calculate the following, the resonant frequency. So from this information that we have, what is going to be our resonant frequency in this case? So take note that the resonant frequency is given also from your formula sheet. That's 1/2 pi the square root of LC. All right. So no matter the way that you are given, as long it is the resonant frequency, you work with only inductance and capacitance. So take note for that. That is our resonant frequency is going to be 1/2 pi times the square root of our L, which is the inductance, which is 5. So that is 5 times the capacitance. In this case, our capacitance is 250 nanofarad. That is times 10 to the exponent of -9. That's a nanofarad. So this is going to give us the resonant frequency in this case. So if you are to simplify properly, you are going to obtain 142,3525, which is going to change into a 3. That is in what? In hertz. So this is your resonant frequency in this case. So that was actually 2 marks for that. 3/2, which is 2 marks. Then the dynamic impedance, which is ZD. Also, we can have this given from our formula sheet. So that's an advantage of also because it's an application of what you're already given in this case. So remember that our dynamic impedance is given as L/RC, whereby we have everything in this case. Our L, which is our inductance, we have it as 5 over the resistance of the circuit, which is our resistance in this case. That is 25 times the capacitance, which is at 250 nanofarad, which is to the exponent of what? Of -9. So this is going to give us the dynamic impedance in this case, which is ZD. That's 80,000. So this is going to give us 800,000, not 80,000, but 800,000 ohms. All right. So you can have it in kilo ohms. If we divide by 1,000, that will be 800. So this is going to be 800 kilo ohms in this case. All right. So that is our dynamic impedance, and from there we need the current at resonance. So the current that is at resonance, that is the total current in this case. So if it is at resonance, it is going to be from the voltage over the dynamic impedance, which is our total impedance for this circuit. So that is how we can have our total current. So that means we can say that our total current, which is 2.33, is taken from the total voltage over the dynamic impedance in this case, which is our total current is going to be the total voltage, which is 12 volts. In this case, we've got 12 volts as our supply voltage. So that's 12 over the dynamic impedance, which is 800 kilo or 800,000. So that is 800 kilo or 800,000. So this is going to give us the total current of the circuit, which is that's 0.000 4 zeros. All right. So that's these are 4 zeros, amps. All right. So this is in amps. So you can even write this the best way, because even if you write in milli, it is going to be 0.015 milliamps. So it's best for us to write in micro amps. So remember, micro, that's to the exponent of -6. So for you to convert to micro, you multiply by the inverse of 10 to the exponent of -6, which is 10 to the exponent of 6. So if you multiply by 10 to the exponent of 6, you are going to obtain 15. So we are going to have 15. So that answer is now in micro amps. So this is our current in amps. So this is going to be micro amps in this case. All right. So that was the total current in this case of from the current when it is at resonant in this case. So that's 6 marks for everything, having a total of 23 marks from this question paper. So these are the typical questions that you have to expect from your finals. A combination of AC and DC on the same question. This is how they are now asking this question, just like the previous way they used to do from these question papers. So we have to be very careful, work with DC, and also understand your AC at the same time. That can help you improve your marks. For now, that's it, guys, from Maison African Motives. Till we meet again.